I'm here to explain the theorem. There are four different possibilities, but I'll just summarize it with f, which goes from A to R, is continuous at a point C if and only if all sequences in the domain, f of that sequence is going to converge to f of C. Well, here's kind of an explanation. Let's take a look at an example here. F of x equals x squared. That's continuous at the point 2. What does that mean? That means if you take any sequence, 1, 2, 3, 4, 5, 6, right? They're all, and so on and so forth, is converging to 2. If you look at what these map to, here's f of x of 1, here's point 3, here's point 2 up there. So it goes 1, 2, 3, 4, 5, 6. Notice that the red sequence is converging to 2, and the blue sequence is going to be converging to f of 2, which happens to be 4. I think you might be able to imagine that no matter what red sequence I pick down here, when I map it up to the green line, it's always going to be close to 4, which is f of 2. There's no way to kind of get around that. Let's contrast that with over here. This is my non-example. F of x equals 1 if you're bigger than or equal to 2, and negative 1 if it's less than 2. So certainly, you know, right, f of c equals f of 2 equals 1 in this case. So certainly I could come up with a sequence 1, 2, 3, 4, 5, 6, etc., that does map up to here 1, 2, 3, 4, 5, 6, and the blue things would converge to f of 2, which equals 1. But it has to be true for every sequence. So if I take a slightly different sequence, say in orange, 1, 2, 3, 4, 5, 6, and see where it maps. Let's do this in dark blue here. Right? We do 1 maps there, 2 maps there, 3 goes over here for some reason, but that's perfectly fine. 4, 5, 6. As long as the pattern continues as it approaches 2 from the left, that's going to be a sequence that does not go to f of 2, since it's going to negative 1, which is not f of 2. So this is, in 119, you would have characterized this as basically the limit from the left has to equal the limit from the right. Basically, it doesn't matter what sequence you choose, whether it's from the right or left, it's perfectly, you know, you're going to converge to f of 2. And finally, last example is here. So this is not continuous to 2. This is not going to be continuous to 2 too, because you get a point 1 if it's rational, 2 if it's not, or 0 if it's not. Right? Again, you look at some sort of a sequence, 1, 2, 3, 4, 5, 6. Notice it's even difficult it's tough to even tell where to map it, because you're not quite sure what a sub 1, a sub 2, a sub 3, etc. are. So instead, let me give you a formula. Let's say, right, if a sub n equals 2 plus 1 over n, well, these are all rational. So f of a sub n is going to equal f of 2 plus 1 over n. Oh, but that's f of a rational number, so that's going to be a bunch of 1s. That's going to converge to 1, which equals f of 2. Here's another one, right, if b sub n equals, again, 2 plus 1 over pi to the n, that's going to converge to 2, as we needed. But f of b sub n is going to be equal to f of 2 plus 1 over n squared, 1 over pi to the n, sorry, which is irrational, which means it's going to be a sequence of zeros, which is going to 0, which is not equal to f of 2. So basically, if you can find a sequence that maps to 2 that doesn't map in the f space, f of that sequence doesn't map to f of c, then it's not continuous. So this is really more useful to tell you why something is not continuous rather than why it is.